Hello everybody, my name is Marco Tartagni from the University of Bologna, Italy, and in this video tutorial I will show you something a little bit unusual in sensing and sensor design, and specifically how information theory could help the designer in the optimization of the acquisition process. The main objective of this talk is a relationship between information theory with measurement sensor design. Thus, I will present new viewpoints for defining a sensing process, and I will introduce, with no mathematical insights, some tools for a quantitative characterization of a signal acquisition chain. Finally, I will make a very simple example of practical application, showing how abstract theory could lead to simple results. What is the best resolution of an A to D converter for a noisy interface? Then we will find the answer. Let's talk about interesting viewpoints of the sensing process. This slide shows a very general representation of a sensor. Sensors should not be considered as simple transducers followed by a quantizer. In complex systems, raw data processing is required. For instance, machine learning algorithms are examples of this higher and final level of elaboration. Even if the tasks of these two blocks seem completely different, they should be considered as belonging to a unique process. The common goal of any sensor processing stage is the extraction of an essence of the final task of the measurement process. We will call this thing information. However, information theory could better quantify this as mutual information. Thus, sensor is an information classifier. The information is extracted, passing through each stage with unavoidable losses due to noises, interface errors, or even computational errors. We cannot increase mutual information. This concept reminds the entropy of the second principle of thermodynamics. Design optimization means to minimize losses from the input to the output, but there is a fundamental limit in all of this. One of the main issues in sensor design is that all data are intrinsically stochastic, and they could be analyzed as distributions in time and space. For example, a signal could show a value or space distribution and a frequency or time distribution, as well as noise could be modeled with the same representation of two distributions. Information theory was born in the telecommunication area, where the original goal was to transmit as much information as possible through a channel. Optimization is mostly made on encoding functions on fixed channels. The same concept could be applied to a measurement system, where instead data are fixed, and optimization could be done by the interface that acts as a channel and encodes data. Now, let's make an extremely concise introduction of two concepts of information theory: entropy and mutual information. Here it comes a first concept of information theory: entropy. Using the sensor channel paradigm, we can devise distributions for the input, for the noise, and for the output. Information theory shows how for any given distribution we can associate an entropy shown in this expression. The entropy is bounded by a maximum given by the uniform distribution. Now, let's introduce a second fundamental concept: mutual information. Mutual information is the difference between the output entropy with the conditional entropy. But what is conditional entropy? It is the spread of noise distribution mapped into the output for a given input. If the conditional entropy is constant, then we can simplify the previous expression where the second term is the noise entropy. Assuming that the noise entropy is constant or negligible, to maximize the mutual information, we must maximize, by way of the input-output relationship, the output entropy in order to have a uniform output distribution. The maximum possible mutual information for any possible input-output relationship Fx is referred to as channel capacity, and it is a bound limit of the entire system. And this is the expression of the channel capacity of our system. Here we have two important results from information theory analysis of the acquisition chain channels. First, the maximum mutual information or channel capacity that can be reached by a noisy interface, either analog or analog to digital, is given by this expression, where FSO is the output full scale and sigma n is the RMS noise. Thus, noise fixes the amount of information that could be achieved, and of course, this value is the result of an optimization of the system, and it cannot be overcome in any way. Second, mutual information could be used to redefine the concept of resolution, which is the full scale divided by the number of resolution levels encoded by the mutual information. In this case, resolution is a statistical average considering input and noise distributions. Finally, a very simple application of the information theory-based approach. Now, let's make a very simple example of application of what we have presented so far. Here it is an analog to digital interface characterized by noise and a quantization process. The question is, what is the best choice of quantization levels to maximize the conveyed information? Since noise is present, some least significant bits could be very noisy. Now, is there any sense in adding more bits to increase quantization resolution at the cost of power consumption increase? Or should we truncate noisy bits to reduce power consumption, but at the same time quantization resolution? What is the best choice in this trade-off? Information theory indicates that there is a reference number of bits of the converter for the acquisition process, K star, given by this expression. If we increase the quantization levels beyond that value, we do not increase the conveyed information, but we do increase power consumption. On the other hand, if we decrease the quantization levels below that reference, we reduce power consumption, but also we reduce the conveyed information. This slide shows a simulation of the normalized mutual information at the interface versus the RMS noise over quantization level ratio. It agrees with theory where, for fine quantization levels, this is the expression of the maximum value channel capacity. As shown in the plot, if we increase the number of levels, the information does not increase, as shown in this asymptotic limit of the plot. For coarse quantization, the mutual information is simply k, which is the number of bits of the A to D converter, and decreases as we decrease the quantization levels, as shown in this plot in the yellow line. A corner point between these two regions could be derived and corresponds to the value of k star. Conclusion: any effort to make quantization finer than a fourth of the noise standard deviation is useless because it does not increase conveyed information but increases power consumption. Thus, it is better to choose the number of the A to D converter bits slightly higher than k star. In a summary, the concept of information theory could be effectively applied in a measurement process and sensor design. This approach leads to simple and useful guidelines in practical application cases. Many other results could be found using this technique, such as the optimization of signal acquisition chains. Finally, a brief list of papers and books about what I have presented so far. And thank you very much.